Alright, in this problem we are asked to find the orthogonal trajectories of the family of curves of x equals k times y squared, where k is an arbitrary constant. Now that function there, that gives us off to the right here, I have graphed all these sideways parabolas emanating from the origin. So x equals k times y squared gives us a bunch of sideways parabolas. But what's this question asking? Find the orthogonal trajectories. Orthogonal, another name for perpendicular. So essentially, I'm trying to find some function that every time it intersects with our blue lines here, so every time it intersects with our sideways parabolas, it's going to be orthogonal to it, or perpendicular. Now on this graph, I also have graphed what's going to be turned out to be our answer. It's going to be a whole series of ellipses. And you notice every time that those red ellipses intersect with our sideways parabolas, it forms a right angle, or it's perpendicular to it. Every time they intersect, even going in, every time it is perpendicular there. So those ellipses are the orthogonal trajectories. I gave us the answer there, but how do we get there? How do we find the equation of those functions? Well, first, let's think about this. So perpendicular trajectories. So we are looking for functions that are perpendicular to our parabolas. And when I think of perpendicular, that's a lot associated with slope. So I need to find the slope of those parabolas. That's kind of my first step. I need to know the slope of my blue parabolas here. I need to know the slope of these at any given point, because I need to know the slope of them in order to figure out something perpendicular to them. So how do you find the slope at any given point? The derivative. So I'm going to take the derivative of both sides, so derivative with respect to x of both sides, and on the right side, that becomes a nice little 1. The k is a constant, so that pulls out, and then we have implicit differentiation, because I'm taking the derivative of y with respect to x. So my derivative is 1 equals k times 2 times y times dy dx. Not necessarily my derivative, because I want that solved for dy dx, so I know what the slope actually is. So I'm going to bring everything except dy dx over to the other side. So I have 1 divided by 2 ky equals dy dx. Okay, nice. So we see there we've got the slope. So at any point on our curve, our slope is 1 over 2 times k times y. But there's a problem here. And this is a problem with our orthogonal trajectory problems a lot. This problem is reliant on k. So it depends what k value. It depends the k value that affects which of these parabolas I'm actually talking about. So I want to get it not in terms of k. I don't want it dependent on k. So I think, is there some way I can substitute in for k such that my slope, my derivative, is only in terms of x and y? Turns out there is. Because look what we're given up top. X equals k times y squared, which means k is equal to x divided by y squared. I can solve for k there. Thus I will take this guy and put him in for k in my derivative. So I have 1 divided by 2 times x divided by y squared times y equals the derivative. So we will just clean this up a little bit. I can cross out a y up here with a y down there. And then notice I have 2x divided by y in the basement, so I will multiply top and bottom by y, and I reach y over 2x equals dy dx. So this is telling me that any point on my parabolas over here, the slope is y divided by 2x. But we need to find the orthogonal slope, so the perpendicular slope at any point on the parabola, because that will be the slope of our solution, whatever that turns out to be. And so going back to our early algebra knowledge, we know that the slope, the perpendicular slope to a slope, is the opposite reciprocal. So what is, if this is my slope m, the perpendicular slope is 1 over m negative. So negative 1 over m. So essentially that's saying we're going to take our slope, we're going to take our derivative, flip it, and make it negative. So we are going to deal with this guy right here. My dy dx now is going to equal negative 2x over y. So that's going to be the slope at any point on my solution curves. But what's my solution? Well, right here I have a differential equation, and I need to find the solution. I need to find the function that gives me that derivative. And in order to do that, I'm going to need to take the integral of both sides. But before I do that, I want all my terms to be the same. I want my y's over here, my x's over here. This is what we call a separable equation. So I'm going to get my y's on the left side. So I'm going to multiply both sides by y, and I get y dy equals, and I'm going to bring that dx over by multiplying by dx, so negative 2x dx. And with this here, I have my y's on the left, x on the right. I can now take the integral of both sides, sort of like performing a mathematical operation, just like if you multiply one side, you multiply the other. Take the integral of the left, integral of the right. You can think of it in that terms. So I integrate the left side, and it is y squared divided by 2. And then it equals negative 2x squared divided by 2, a couple power rules. But where's the plus c? This is an indefinite integral. Think about this for a moment. So on the left side I took an integral, so I could say plus c sub 1. On the right side I could say plus c sub 2. But then let's combine our constants. So I would subtract c sub 1 from the left side, and on the right side I now have c sub 2 minus c sub 1. But these are all just arbitrary constants. We haven't specified a value of c, it's all arbitrary. So instead of having two c's floating around, we can just relabel c sub 2 minus c sub 1 as our c. So that's a thing we can do if we have integrals on both sides. We can essentially just add that 1 plus c. And then to clean this up a little bit, we can cancel out those 2's, and then I can move that x term over. So I have y squared divided by 2 plus x squared equals c. Rewrite that x. This is the equation for an ellipse. Y squared divided by 2 plus x squared equals c, where that c will be kind of how big or how small the ellipse is. And we see that that makes sense with our drawing. At the beginning I said those red curves were the solution curves, and it turns out that we got it. We got the function that matched up with those ellipses. So this is saying at every point on our blue parabolas here, every point that our red ellipses intersects with them, it's perpendicular. We found the orthogonal trajectories to that family of curves x equals k times y squared.